Welcome back to my Intro to Python tutorial series. So this is where we were at the end of the last video. We have a function isPrime, and it takes an argument x. It checks if x is equal to 1. It goes from 2 up to x minus 1 and checks if it can divide by any of those numbers with 0 remainder. If it can, it knows that x isn't prime, and it returns whether or not x is prime. So we're running this from 2 to 100, and it gives us good answers. If we run it from 0 to 100, we see that it says that 0 is prime, because it's just not even getting into this loop at all. So we can add an explicit check here, or x equals 0. Cool, so if we want to do this up to some large number, we're going to go through 10,000 iterations here. And each time through, we're going to go from 2 up into the number that we're passing in and check whether it's divisible. This ends up being quite a few operations pretty quickly. So it turns out there's actually a much better way to do this. We're going to start out with some number that we want to go up to and a list of true that long. So this is going to give us a list 100 long of true, and I'll show you what that looks like. If this was 10, then we'd have 10 trues here. Cool. So we're going to go through our list, and we're going to say primes 0 equals false, and primes 1 equals false, because we know that we want to explicitly check for them. So we're going to go through this list, and if we see a false, we're just going to continue on. If we see a true, like we do here for element number 2, remember this is 0, 1, 2, then we're going to mark all of the multiples of 2 as false in here. Because we know if we find a true, the number's prime, but even though 2 is prime, that means that 2 times 2 isn't prime, 2 times 3 isn't prime, 2 times 4 isn't prime. And we're going to go through all the way up to the end of the list, marking off the multiples. Then we'll look at 3, and we'll see true. So we know that 3 is prime, and we'll mark off all the multiples of 3. We'll already have marked 3 times 2, because that's equal to 2 times 3, so you can start at the number squared and go up to the end of the list. And that means that when we get to 10, we'll check it. We'll see, first of all, that it's not prime. But even if we tried to mark off all the multiples of 10, our first one would be 10 times 10, which is the end of the list. So at 11, we don't even need to check, because we've already marked off everything we could possibly mark off about it. So we can stop at somewhere near the square root of the list. So let's say for I in range from 2 through to n, which is going to give us n minus 1. So this will be 0 to 999. Sorry, 0 to 99. It'll be 999 if we had 1,000 here. We're going to say if primes I is false, then continue. What this will do is it means that whatever we put here, it'll skip. It'll just go back up to the top of the for loop and continue on for the next value of I. We don't need this else because we can't get here if we've hit this part of the code, because the continue will just shunt us through, but it makes the code a little more readable, so I'm going to put it there. So if we get here, we know first of all that the number at primes I is prime, and second of all that we need to mark off all the multiples of that number starting from the number squared as false. So we'll define another number that starts at the number squared. So for 2, this will start at 4. We'll say primes j equals false. And then we'll increment our number by I. And we remember that when you're doing this, shorthand for j equals j plus I is just j plus equals I. And we'll want to do this in a loop. So we'll want a while loop saying while j is less than n, go through and mark off all the multiples of I as false. So at the end here, we should get out a list of trues and falses with trues where the primes are. So let's print that out in a little more reasonable way. So let's say for I in range up to n, Now we could say print string of I plus is prime question mark plus string of primes I. And that should work unless I've got any typos. Great. But there's another way to do this which is a bit easier. So Python has what are called f strings. So we can put something in a string and we can print it. But if we put squiggly brackets in here, then it'll evaluate whatever's in those squiggly brackets and print that out. So we could print out I, we could print out I times I. You can have statements in here as well as just variables. So what we want to do is say is I prime, and then print out primes I. Cool, so that's just a bit of an easier way of handling your outputs rather than having to put pluses in strings. So we can see 0 and 1 are not prime, 2 and 3 are prime, 4 isn't, 5 is, 6 isn't, 7 is. Great. So printing out all of this stuff actually takes quite a bit of time, and we're about to look at what happens if you start to make this a bit longer. So for 1,000, it shouldn't take too long. Looks like most of that time there was going to be, the compiler just kind of not starting. But if we wanted to, it's also cut us off here. So if we wanted to run through and see how long it's going to take to do some bigger ones, let's just print out the last one, right? So the last number we're going to do, this is going to be 0 through 999. So the last number is actually going to be n minus 1. And we'll print out primes n minus 1. So this tells us that 999 is not prime. So if we run it for 10,000, that was pretty quick. We run it for 100,000, that was also pretty quick. So we can see that this approach, that took a little bit of time. This approach is a lot faster than going through and doing order of n squared operations. If we do this, it's going to start to take a reasonable amount of time. But we'll also have checked all of the numbers up to 9,999,999 to see whether they're prime. So that's pretty cool. We did say, though, that we don't have to go all the way up to n. So right now, we're going all the way up to 999,999. Instead, we can go up to square root of n. If we wanted to do that, we're going to need the math library. So we import math, and math has some functions. We use them by doing things like this. So I'm just going to cut this for a second, and we're just going to print square root of 10 so that I can show you what I mean. And math has another function called sealing, or seal, which gives you the number above, returns an integer, returns the integer above the floating point here. So if we pass in 10.0, it'll give us 10. But it's just round up, basically, to the nearest integer. So if we do the sealing of math.square root 10, cool, we get 4. And if we take a look at what we're going to have to go up to do 1,000, we only have to go up to 32. So that's pretty cool. I'm just going to Control Z all the way back to get my program back. So down here, we can go to math.seal. So it's EIL, math.square root of n. Just checking my brackets. So now when we run, this should be a lot faster. Let's comment this out. Let's go back to printing them all out just so we can see what happens. And we can see we've still got our same answers here. Down the bottom, we've still got a whole lot of falses, so we've been successfully marking things off. This has not printed out correctly, but that's fine. And if we take a look at what happens for large numbers now, get back this last one, we can see 10,000 should run pretty fast, 100,000, million, 10 million. So it's still taking a while. This feels like longer than it should have been, though. but it'll still be running quite a lot faster than it was before. So that is the Sieve of Eratosthenes. I'll put a video down below to a visual representation of how it works, somebody explaining it with some nice graphics. So if you haven't quite got your head around what's happening here, that could help. So next video, I think we're actually getting to about the limit of where you want to be with some online Python compiler. We're going to go through how to install Python and Visual Studio Code and get yourself set up using Jupyter Notebooks, which is a nice environment that lets you see what you're doing.